Hi, in this video we will review the concept of optical flow and how to use it to detect motion. With optical flow, we refer to the changes in the pixel values of a pair of images regardless of what was the real cause of that change. Ideally, when you set up a camera system, you try to avoid the situations we discussed in the previous video. So, we have two images that were taken quickly one after the other. The first one on a time t and the second on t plus delta t. And we're going to focus in one point. Let's say a point in the paw. In the first image, the point has coordinate x, y. And in the second image, the same point is now on x plus delta x, y plus delta y. Then the optical flow is given by delta x over delta t, delta y over delta t. And as you might be thinking, this can be easily calculated using the finite difference. This works under two closely related assumptions. The first one is that delta t is really small, so the pictures are close to each other on time, and the second is that the intensity values of the region of interest do not change. In other words, the paw should keep the same structure and intensity between the two images. If we have drastic changes in the illumination or shape in the objects from one image to the next, then the calculation will fail. This doesn't mean that in a video there's no illumination changes, but we need some constancy at least between every two images. Okay, let's assume that our images fulfill those requirements. And let's call the optical flow UV. We can rearrange the formula to create the optical flow constraint equation. Here, Ix, Iy, and It are the derivatives on each direction. So let's see an example of how we calculate this using the finite difference. We have the two images stacked one over the other. For a given window, we can take the average of pixels inside this window and subtract the average of the same window on each dimension. For example, for delta x, we can calculate the average value of the window in x and then subtract that from the average value in x plus 1. We do the same for y and for t. And then we have the optical flow of our window. It sounds really simple, but this might not work in every scenario. Here an example. Imagine that we have this object that moves between images. And it's clear that the movement was from the upper right corner to the lower left corner. And this is the same for all the objects. But when we calculate the optical flow, we use a small window that basically is constraining the amount of information that we have. And what we see is that the optical flow goes up. Then we need a better method to get a more accurate estimation. Here we can use the Lucas-Kanade algorithm. So we know the optical flow constraint. So instead of calculating the average of the window, we can take the intensity of each pixel within the window and create a linear system like this. Here, we are just moving the derivative of time to the other side of the equation, and we end up with a matrix A that is formed by the points within the window. So if the window is size n by n, then A is n squared by 2. Then we have the vector UV, and all of this is equal to v that contains the time derivatives that should be n squared by 1. Now we can solve this system using least squares, using the pseudo-inverse solution. So we know that U equals to A transpose A inverse A transpose B. That is simple and fast to calculate. But like every approach, it has its own limitations. The matrix A transpose A needs to be invertible. In practice, this means that the pixel values within the window have to be rich, have texture, and be variable. If all the values within the window are similar, the inverse of A transpose A will be rank deficient, and your program will complain. There's not much that we can do here. Even for us, if we move a white piece of paper and we look only through a small window, we won't be able to see any movement. So having a rich texture in the image will help substantially for the motion detection. But we still have the problem of the window size. Remember that one of the assumptions we use for the optical flow constraint is that the changes between images should be small. Then larger objects or objects that are moving really fast between images will result in an accurate estimation. We can solve this problem applying the trick of the pyramid of Gaussians. If you remember, in SIFT, we create a set of copies of the original image to compare on different scales. Here we can use the same approach. We can reduce the resolution of the original image by the half every time, and in this way, high differences become small in the low resolution. For example, let's say that the difference between this point and the new location in another image is 10 pixels. However, if we reduce the resolution of the images in half, then the difference in the location will be only 5 pixels. If we keep going, eventually the difference between the initial position and the next one will be only 1 pixel. And then we are not violating the optical flow constraint. Then the method is start by the lowest resolution images, and we calculate the optical flow. Then we will take the next level of resolution. But here we apply the optical flow that we computed in the first step to warp the image. With this, we are including the motion that we found in the first step. Now we calculate the optical flow again, and we repeat the procedure. We take the first image of the next level and we warp it using the combined optical flow computed in the previous level. And we calculate the new one until we finish. This method works really well because we are propagating the calculation of the optical flow at different resolutions, and the results are more accurate compared to computing the optical flow only on the original images. Okay, in this video we talk about optical flow. We review the Lucas-Kanade method and how we can improve the computation of optical flow by looking at different scales. See you in the next video.